So up to now I have discussed that why Buckingham Road is very essential in case of circular road or circular track. Okay. So now we'll take another example, that motion in a vertical circle. This is motion in a vertical circle. Okay. In earlier case, what I have given an example, that suppose you have tied up a stone with a rope or string and rotate it. Okay. Earlier example was for vertical. Rotate the stone in a vertical circle. Okay. Rotate the stone in vertically. Okay. Sorry. Rotate. In this example, we rotate the stone in horizontally. Okay. In earlier example, we rotate the stone by grabbing the other side of the rope in a horizontal circle. Okay. So here the centripetal force is exerted by the tension in the rope. Okay. Tension will be equal to centripetal force in this case. Okay. For rotating a stone in a horizontal circle. Okay. Now this example is for motion of a body in a vertical circle. Okay. Suppose you have tied a body of mass m. Suppose you have tied up a body of mass m with a string or rope. Okay, you have tied up a body of mass m with a string or rope, and you rotate it in a vertical circle. Okay, in vertical circle. So what happens? You have rotated this in this way. Okay, so at some time or at some instant, it will be the position of this mass will be in vertical opposite direction. Okay, in this. At certain instant, the position of this mass will be here. Okay, so we have to calculate the velocity. Okay, we have to calculate the minimum velocity. Okay, minimum velocity. Suppose it is v. Minimum velocity of, suppose it is at this point, velocity of this mass is v1. Okay, v1 is the velocity of mass m which is rotating as vertical circle. Okay, in a vertical circle, and mass, suppose mass m is rotating in a vertical circle, and initial and velocity of this mass at the lowest point is v1, and suppose the highest point velocity is v2. We have to calculate what is the velocity at the highest point. What is v2? We have to calculate. Okay. Now suppose, now see what are the forces. Okay, what are the forces that are exerted on this mass at this position. Okay, so this one at position, at the lowest position, what are the forces that exerted on this mass? First force is acceleration due to gravity, mg. Okay, now next force is tensional force. Okay, this pulling force, okay, towards the center. This is the cause of centripetal force. Okay, due to this tension it can rotate in a circular path. Okay, so this is the cause of centripetal force, this tension in this case. So see, at this position, in the lowest position, what will be the centripetal force? Fc. Fc will be T minus mg. Okay, or you can write m v1 square, velocity at the lowest position at this position is v1, m v1 squared by r is equal to t minus mg. Okay, suppose you are taking this number 1. Now you are asked to calculate the velocity v2. Okay, so see, in this position, okay, at the highest position, what are the forces applied on this body or applied in this mass m? So first force is tensional force. Okay, tensional force. Suppose this is T1. Okay, T1, and this is T2. Okay, because see, at this position, the potential energy of both the kinetic and potential energy of this mass changes. Okay, so that is why tensional force at this position and at this position, both the position will be different. Okay, in case of rotating a mass or a stone in a horizontal circle, tension is uniform at this position. Okay, this position of the stone. But in this case, see, due to the gravitational force, at this position the potential energy or the kinetic energy of and potential energy will be different, and this position also the kinetic energy and potential energy also be different than this position. So I consider tension in this position is T2 and at this position tension is T1. So here see, the centripetal force is towards the center and the forces that is exerted at this position are T2 and mg. Okay, so what we get in this position, suppose this position A and this position B, at position B, at B position, centripetal force will be what? T2 plus mg. Okay, or m v2 square by r is equal to T2 plus mg. Okay, now okay, so this is question 2. Okay, so see, what we are asked, we have to calculate the velocity v2. Okay, the minimum velocity we have to calculate the v2 minimum. Okay, that is minimum velocity that should be given to the object or of mass m such that it can complete the circle or complete the circular path. So what will be the minimum velocity at this position, okay, for this mass? So we have to calculate v minimum. So we have m v2 square by r from equation 2. Okay, from equation 2 what we have m v2 square by r, and this into T2 plus mg. Okay, this is we have. So see, at this position two forces are applied. Okay, two forces are applied towards the center, tensional force and gravitational force. Okay, so if this cannot be 0. Okay, there is always gravitational force, but you can diminish the tensional force. Okay, so if in minimum case, if T2 is equal to 0, then what will be? Then V2 will be minimum. Okay, if T2 is 0, then V2 will be, then velocity at this position will be minimum. Okay, so the centripetal force, if T2 is 0, the centripetal force at this position is exerted by the gravitational pull mg. Okay, so we can write it for minimum V2 minimum will be how much? So V2, so sorry, I'm writing this. M V2 square by R is how much? After putting T2 is equal to 0, M to 0. So M of cancel. So V2 will be RG square half. V for RG. So this is the minimum velocity. Okay. So V minimum at position 2 or V2 minimum will be root over RG. Okay. So see, this is the minimum velocity that should be given at position B to make the body rotate in a vertical circular track. Okay, so this is the minimum velocity that should be given, that have to be given at position 2 or position B, such that our body can move in a vertical circle. Okay. Similarly, we can also calculate what is V1 minimum. Okay, what is the minimum velocity at position A? Okay, to complete this vertical circle. Okay, we can also calculate what is the minimum velocity at position A such that our body can move or our body can complete this vertical circle. For this, we have to know, or we have to, for this purpose, we have to know about the conservation of energy. Like conservation of momentum, there is also another thing, conservation of energy. So first thing, we have to learn about conservation of energy before calculating V1 minimum. Okay. So I've solved this problem as this. Okay. By simply considering the centripetal force, okay, we can calculate what is the minimum velocity at the position B, such that our mass, body of mass cell can rotate in a vertical circle. Okay, so this is the minimum velocity. Okay, the minimum velocity at position B for completing a vertical circle. Okay, so this is another example regarding centripetal force. So in this chapter, what I've discussed up to now, in the fifth chapter, first thing we discuss about the force. Okay, here we get three laws: first law, second law, third law. First law about inertia. Second law is about F equal to ma, about external force. Okay, it deals with the external force. And second law, when external force concept comes, and from here we can calculate the acceleration from net external force. Third law, the cause of this net external force. Okay, the cause, third law tells us what is the cause of the net external force and external force. And from here you get that force always appears in pairs. Okay, forces always appears in pairs. So from this we discuss in the part of force, and from combining between first and second law, we have concluded or we get the conservation of momentum. Okay. Then in the second unit we discuss about the friction. Second unit is about friction. Here we get the cause of friction, that is, it is because of the atomic and molecular attraction between this is because the atomic and molecular attraction between the two surfaces. Between the molecules, atoms, attraction between the molecules and atoms between the two surfaces causes friction. So three types of friction we get: static, kinetic, and rolling. And cause of this friction, let's discuss. In case of steric friction, we get the limiting case mu s also, and is the limiting value of steric friction. And kinetic friction, we represent this as mu k into F. And this kinetic friction value is always less than the limiting value of steric friction. And we discuss about the cause of this rolling friction. Okay, this is caused by the depression caused by circular object in the path or in the road or in the way it moves. Okay, now next thing, and we discuss some problems also. Now last thing in this chapter, chapter number 5, we will discuss the circular motion. Circular motion. Here you get centripetal force, and centrifugal force. Centrifugal force. Okay. Here we discuss about the banking of roads. Okay, this is the important thing to discuss in this chapter, banking of roads. Okay, why banking of roads is essential in case of circular track or circular path. Okay, these are the things we have discussed. And regarding these topics, we have discussed many problems also. Okay, now the next chapter we'll discuss is chapter number 6. Okay, this is work, energy, and power. Work, energy, and power. Okay. Here we get here in this chapter we will get the work energy theorem. Then we will discuss about the kinetic energy. Okay. Then we will get constant force. Okay. Constant. We'll discuss the difference of constant force and variable force. Okay. Variable force. Okay. And calculate the work done in case of constant force and in case of variable force. Okay. Then we will discuss about the power. Okay. Power. And we have to discuss about the collisions between two bodies. Okay. Collision are elastic, inelastic, and there are different cases. Okay, we'll discuss. So before going to the chapter, you have to know about the product of vectors. Okay, we'll discuss first the product of vectors. Okay. Product of vectors. So earlier we have discussed the addition and subtraction. Earlier we have discussed about the addition and subtraction of vectors. Okay. Now we will go for product. Okay. So there are two types of product in case of vector. One is scalar product. Scalar product or dot product. Then second one is vector product. Or cross product. Okay. In case of when you discuss the product of vectors, okay, there would follow there are two types of products. Okay, in case of vectors, there are two types of multiplication of products. Okay, one is scalar product and another is vector product. Scalar is also called dot product, or it is called also cross product. So in case of dot product, suppose there are two vectors. Okay, so there are two vectors A and B. if we do the dot product of scalar product, then what we get? AB will be a scalar quantity. Scalar quantity. Okay. If we go for that scalar product or dot product is represented by A dot B. And if we perform vector product, which is represented by A cross B, then we get a vector quantity. Okay. Product of scalar product of two vector is always a scalar quantity, and the dot product and the cross product of two vector is always a vector quantity. Okay. Now here you only need to know about the scalar product or dot product. Okay. So how we represent the scalar product? Okay. Suppose A dot B. Okay. Scalar product of two quantity A dot B. How we write this? AB cos theta. Okay. Scalar product of two vectors A and B is written as AB cos theta. A dot B is equal to AB cos theta. It is a scalar quantity. AB cos theta is a scalar quantity. So this is what, suppose this is a vector B and this is vector A. Okay. So A dot B means what? A into B cos theta. Okay. B cos theta means what? This is, suppose there are two vectors A and B making an angle theta between them, and A dot B means what? The scalar product will be what? AB cos theta. Means A means what? B means magnitude A. Okay. A means magnitude of vector A, and B cos theta means projection of B on A. Okay. What is the projection of B on B on A? Okay. So B cos theta means A into magnitude of vector A into projection of B on A. The projection of B on A means this O, suppose I am dividing this OP. Projection of B on A is OP. Okay. And OP will be how much? OP is OQ cos theta. Okay. OQ means B cos theta. So this is how I reckon. So dot product is nothing but A dot B is AB cos theta means A into the dot projection of B on A. Okay. So this is the dot product. Okay. Or you can that there are certain properties. Okay. Properties of dot product. They are commutative. Okay. This A dot B, you can write it as B dot A. Okay. It follows commutative law. Okay. That is A dot B is equal to, that is A dot B, you can write B dot A. Okay. This thing you can also write that B into projection of A on B. Both are same thing. Both will give same result. Okay. Now second property is distributive. It follows distributive law. That is, you can write, suppose three vectors A, B and C are in this way. A dot, suppose there are three vectors A, B and C, then A dot B plus C is equal to A dot B plus A dot C. So these are distributed. So dot product is distributed. Okay, or we can write that suppose A into lambda into B. Okay, suppose lambda is a constant. Very constant term. Okay, and we can write this as lambda. We can take outside lambda into a dot product A dot B. Okay, we can also write in this way. So these are some properties regarding dot product. Okay, now next thing is we have learned about the unit vectors now. Okay, suppose there is a vector A is how much x, or how you can write a vector A x I cap, a y j cap, and a z cap. Okay, suppose there is 3-dimensional system x y j. Suppose there is a vector A. Okay, so how you can write this? A x I cap, a y j cap, and a z cap. Okay, so Ax is the component of a along x-axis, Ay is the component of a vector along y-axis, and Z is the component of vector A along z-axis. Okay. When in terms of in terms of vector, we assign these unit vectors. Okay. We assign these unit vectors along these components. I is the unit vector along x-axis, A is the unit vector of y-axis, A is the unit vector of z-axis. Okay. So and and another thing is that I, J and K are mutually perpendicular to each other. Okay, what is the direction of I, J, K? To the x, I, and z axis. Okay. So this is the direction of I vector. This is the along x axis. This is the direction of J unit vector, and this is the direction of K unit vector. Okay. Direction of unit vector I cap is along x axis, along, and j cap unit vector direction is along y axis, and direction of k cap is along z axis. So I, J, and K are mutually perpendicular. Perpendicular to each other. Okay. So they are mutually perpendicular to each other. Okay. So we get the unit vectors I, J, and K, okay, along x, y, and z axis. Okay, these are mutually perpendicular to each other. So what will be the value of I dot j, dot product of I and j? So see, the unit of I is, this unit vector means I is called I, J, K, these are called unit vector means the magnitude of each of them. Okay, I, J, or K, magnitude will be 1, and direction is of I is along x axis, direction of j cap is along y axis, and k cap is along z axis. So unit of each of them, magnitude of each of them is 1. Okay, unity. So what is the I dot j? Okay, so it will be magnitude of I, magnitude of j into cos of angle between them. What is the angle between I and j? What is the angle between the I and j? It is 90 degrees. So what will be this 1 cos of 90 is equal. So dot product of any two unit vector is always 0. Similarly, j dot k 0 is 0, and similarly k dot I is also 0. Okay. Now suppose dot product of two similar unit vectors. Okay. Suppose I dot I. So how much? Magnitude of I is 1, and angle between them is 0 degree. So dot product will be how much? 1. Similarly, j dot j is equal to k dot k is also 1. Okay. So here we get dot product of two similar unit vectors is 1, and dot product of two different unit vectors. Okay, different unit vectors is 0. So this is a thing regarding dot product. So how we perform dot product. Okay, now we discuss how we perform dot product. Suppose there is a vector a equal to x I cap plus ay j cap plus az k cap. And another vector b is bx I cap plus by z cap plus bz k cap. And a dot b will be how much? See, a dot b means we have to multiply each component of x, each component of a with each component of b. But one thing we have that I dot j will be 0, j dot k will be 0, and k dot I will be 0, and they are commutative. Okay, reverse of them also will be 0. J dot I will be also 0, k dot j will be also 0, and I dot k will also be 0. So see, during this multiplication, ax into bx, when we perform ax into bx, I am writing bx into bx. I cap will be how much? I cap dot I cap is 1, like we have discussed previously. So it will remain ax into bx plus ax into by. Okay, ax by means ax into by and dot product of I and j. So dot product of I and j will be with 0. Okay. Similarly, ax into bz, this time and this time will give the product of I and k, so it will also 0. So from here you can see that all the terms, okay, all the terms containing different unit vectors, okay, different unit vectors, all the terms where the product is performed. So from here you can see that all the terms, okay, all the product terms containing different unit vectors, okay, will be 0, and all the remaining terms after that. So the remaining terms will be what? The terms is containing the same unit vector. The terms containing the product terms which contain the same unit vectors will only remain. So see, here it is I cap and I cap. So if you perform dot product between ax and bx, so it will be I dot I, it will be 1. Okay, to remain. And see, this is j cap, this is 1. So j cap is also 1, ay into by, and k cap will also be 1, az dz. Now all other terms, okay, all other terms, product terms containing the different unit vectors, containing the dot product of different unit vectors will be 0. Only those terms will remain in which only those product term will remain where dot product is performed between two similar unit vectors. Okay. So this is the result of a dot product. So a dot a is how much? Ax bx. Suppose a is this, b is this, plus ay by plus az. That is, this is how we perform dot product. Suppose I am taking an example. Suppose that there is a vector p is equal to 5 I cap plus 2 j cap plus 3 k. Q is 3 I cap minus 1 j cap plus 4 k cap. So P dot Q will be how much? So the x component of this term, okay, the x component of this term is 5 into 3, 15, then y component minus 2, then z component plus 12. Okay, So result will be how much? Between 27 minus 27. So the product of these two factors will be 25. This is a scalar quantity. So this is how we perform dot product. Okay. If two factors A and B are perpendicular to each other, then dot product will be of A dot B will be 0 because A dot B means A dot B means A B cos theta. If theta is 0 degree, cos 0 degree, this is theta is 90 degree, cos 90 will be how much? 0. So dot product of two perpendicular vectors are always 0. So these are certain properties regarding dot product. Okay. Now there is an example. Okay. Suppose how we calculate the magnitude of the vector. Okay, suppose there is a vector A is equal to x I cap ay j cap plus az k cap. So what is the magnitude of vector A? Okay, that will calculate the magnitude. So in case of this, how we do that? With dot product. So here what we do? We perform A dot A. Okay, A dot A will be how much? X. So see, like earlier we discussed, only in the product term, in the final product term, what the term will remain? Only the term where the dot product is performed with the similar unit vectors. Okay, that is I will the term or component of x will multiply the component of x of another vector only. So ax into ax plus ay into ay if we perform A dot A plus az into az, or ax square plus ay square plus az square. Okay, or A dot A is what? A dot A is what? A dot A is what? A into A, this magnitude, see vector is equal to magnitude of vector is represented by this. Okay. So I am getting magnitude of this into cos of similar vectors of cos of 0. Cos of 0 means 1. So magnitude is A square, magnitude square. So A dot A means magnitude of A whole square. And if we go in this way, A dot A means this. So we have to equate both of them. So magnitude of A whole square is equal to how much? X square plus ay square plus az square. Or what is the magnitude of vector A? It will be root over x square plus ay square plus az square. Okay, so this is how we calculate the magnitude of a vector. So now we get what we get. Magnitude of a vector as a vector is x square plus ay square plus az square. Suppose we give an example. 3i plus 5z plus 3. So what is the magnitude of A? What is the magnitude of this vector? So we simply write magnitude of A is equal to root over 3 square 5 square plus 2 square. So it will be 9 plus 25 plus 4, or it will be 25, 13, 8, 3 over 13. So it is the magnitude of vector A is what? Root over 58. Okay, so this is how to deal with vectors, and this is how we perform dot product case of vectors. Okay, so because when you go for work, okay, when you go for calculating work is what? F dot D. Okay, work is a scalar quantity and it is a product of two vector quantities. These are force and displacement. Force and displacement are two vector quantities. And work is the dot product of force and displacement. Okay, then we get the scalar quantity which is called work. Okay, so work is nothing but scalar product or dot product of force and displacement F dot D. Okay, so that is why before going or discussing about work, we have to know about what is the scalar product or dot product of vectors. Okay, so up to now I will discuss